Alright, so in this video I'm gonna be explaining another important article with the title Graph Pooling for Graph Neural Networks: Progress, Challenges, and Opportunities. So this paper in HK 2023 is very important. Graph neural networks have emerged as a leading architecture for many graph-level tasks such as graph classification and graph generation. As an essential component of the architecture, graph pooling is indispensable for obtaining a holistic graph-level representation of the whole graph. Although a great variety of methods have been proposed in this promising and fast-developing research field, to the best of our knowledge, little effort has been made to systematically summarize these works. To set the stage for the development of future works, in this paper we attempt to fill this gap by providing a broad review of recent methods for graph pooling. Specifically, we first propose a taxonomy of existing graph pooling methods with a mathematical summary of each category. Then we provide an overview of the libraries related to graph pooling, including the commonly used datasets, model architectures for downstream tasks, and open source implementations. Next, we further outline the applications that incorporate the idea of graph pooling in a variety of domains. Finally, we discuss certain critical challenges facing current studies and share our insights on future potential directions for research and improvement of graph pooling. You see an illustrative example of graph pooling. Here, MP is message passing. Pool is just a pooling function. So message passing, pooling function, message passing, pooling function, and repeats many stages. What we need is just a readout from these, so that we can combine all of these readout, which is done after pooling. And so we take a multi-layer perceptron of this augmentation, of this concatenation, for classification. So what we need is a coarsened graph from the original graph G. We provide a coarsened graph so that it has better structural representation, topological representation. So, flat pooling has also known as graph readout operation, directly generates a graph level representation in one step. So output fixed size graph representation when input graphs are different sizes. This is not good. Output the same representation when the order of no input graph changes. So in light of the above discussion, several designs of flat pooling have been proposed. Most of these flat pooling methods perform operations on node representations to obtain graph level representations without consideration of the intrinsic hierarchical structures of the graph, which causes information loss and degrades the performance, because they are ignoring topological information, which is all about graph theory, spectral graph theory, effective resistance, graph random features, personalized page rank, many ideas there are. And so node clustering considers graph pooling as node clustering problem. So we propose a universal and modularized framework to describe the process of node clustering pool. So we deconstruct node clustering into two disjoint modules: cluster assignment matrix and graph coursing. For example, I've explained diff pool, min cut pool, and also SEP. I've described them in different videos. You see, for for the generator, we call it CAM, the cluster assignment matrix. For diffpool, they just use another GNN. But if you remember, MinCut was very good because they replaced the GNN with just a multi-layer perceptron, so it's faster, better computational complexity. And for graph coarsening, diffpool uses this. But you know, the objective of diffpool and MinCut are totally different, because diffpool requires just the original classification and then the auxiliary, but the MinCut, it has something about MinCut objective that in computer science is very important. Of course, they also add other auxiliary losses. But you know, these models, for example, I've explained TopK, SAGPool, ASAP, PanPool. I've explained all of them, attribute pool. I've explained these things in different videos. So it's just scoring. You're scoring nodes. Sometimes you do it with graph neural network. Sometimes just a projection. Sometimes it looks complicated, but the node selector, you get, what is important is you just get the top K scores. And for coarsening, you can use your adjacency matrix is now this, because you have top K index of that. So now instead of n by n, you have coarsened your graph, so it becomes IDX times IDX. The index ranges differently. And then node dropping pooling exploits learnable scoring function to delete nodes with comparatively lower significance scores. If you delete nodes, make sure you don't lose connectivity. So it has some challenges as well. But there are some libraries for graph pooling. You know, you can easily use PyTorch geometric. You can access, if you use PyTorch geometric, then using TU datasets such as protein is just one line of code. Protein, enzyme, DD, NCI1. There are many benchmarks that you see in ICML conferences. Everybody uses the same. Or even if you want to use node classification, use Quora, PubMed, CiteSeer. There are some datasets for node classification. So the above datasets can be classified into 4 categories: social networks, protein networks, molecule graphs, and others. So I've used these in my papers, NCI1, MuTag. What about Quora? Where is Quora? PubMed. And then datasets. Use these datasets. For example, collaboration. And then Quora is here. Quora, CiteSeer, PubMed. These are important for node because it's just one graph but many nodes, as opposed to datasets like this, which is thousands of graphs, but each graph is just around, for example, 20 nodes. For example, this one, thousands of nodes, thousands of graph, but each graph has 20, 30 nodes. Of course, more edges. So I've explained MinCut pool, diffpool, push pool, struct pool, SEP. Um, I haven't explained these things maybe because they are old or they have low performance. And also Top K, this is the very old article, 2019. Sagpool. So, we briefly review recent studies that incorporate idea of graph pooling on a wide range of applications, which can be divided into two classes according to the type of dataset. Structured datasets, where the data have explicit relational structures such as molecular property prediction, molecular generation, protein ligand binding, affinity prediction, 3D protein structure analysis, drug discovery, recommendation, community detection. And then we have non-structured data sets where relational structures are implicit. And the graphs are built according to domain knowledge, such as cancer diagnosis, brain data analysis, anti-spoofing, speech deepfake detection, natural language processing, computer vision. So some methods attempt to handle the node classification with an encoder-decoder learning structure, where the unpooling operation is an important component. Several node dropping methods utilize the unpooling operation, proposing graph UNet. UNet is the great algorithm in computer vision for segmentation. Then they generalize a graph UNet for hierarchical graph pooling. Another important component, the convolution of the decoder term deconvolution. Besides directly adopting convolution of encoder as deconvolution, we can design a more reasonable deconvolution. Inspired by this article, which reconstructs graph signals from smooth node representation from the perspective of spectral domain. Thus, future research directions include handling node-level tasks with an encoder-decoder structure by designing efficient unpooling and deconvolutional operators, developing a unified graph pooling approach through which node-level and graph-level tasks can be simultaneously handled, which is beneficial since different tasks may benefit from each other. The challenge different types of graph is that the graph pooling methods are primarily intended for plain graphs. However, there are also many types of graphs. So several graphs of pooling have been attempted to handle the rarely studied but commonly used graphs in real applications, such as heterogeneous graph, spatial temporal graph, hypergraph. However, the specific graph pooling operators for handling other types of graphs are still lacking. Therefore, we suggest two promising research opportunities: extending existing graph pooling methods or designing new pooling methods to deal with specific graph. And interpretability. Although existing graph pooling methods have achieved excellent results, most of them show little interpretability. This is particularly problematic for drug or disease-related problems. Robustness. Many applications of graph pooling are risk-sensitive: drug design, disease diagnosis. So the opportunity is that although some initial studies have been conducted on the robustness of graph machine learning, few studies have explored the robustness of graph pooling methods. So far, only an adversarial attack framework has been proposed to evaluate the robustness of graph pooling. Therefore, there's much work to be done to develop a robust graph pooling method for practical applications, such as building up comprehensive adversarial attack framework encompasses various types of attacks. And then the large-scale data challenge and its opportunities. Also expressive power, challenge opportunities, also generalized to out of distribution data.